of South Arne chalk for full frame network using new developments in deep computation, etc. And that might sound a bit complicated for some, or a bit too much in one go, but my ambition is to stay easy on the equations and the mathematics here, and try to instead kind of do some intuitive explanations instead of doing it too hard. But what I'm talking about today is some work I did a long time ago, really, but it has not been widely published. So most of what you see here today is also covered in this book, published by Geological Society of London, the Live collection. So me and my co-authors, we did one of the chapters in the book there, it's covering new developments in chalk. And here is the front of our chapter here, and a lot of details, but the important thing here is really to honor my co-authors, which is Donald Stratty, myself, Ole Weibeck, and Gillian White. But just to be, but because this was a lot of work and it was a team effort, so Donatella did a lot of work here. She is from Bologna and she is back in Bologna, but she worked as a geology advisor in Schlumberger for like 20 years, and she was based 15 years in the Middle East in Abu Dhabi, and where she did consulting on the carbonate fields in the Middle East, including Saudi. And then is Ole. He was working in Hess at the time, and so he was working as a geologist on the South Arne field. So he has a really long experience, but in the past he has also worked in academia, and he was a professor in geology in the Geological surveying of Denmark and Greenland for 25 years, so quite impressive. And then it's also Gillian White, which also worked in Hess at the time, but she then went on to Maersk, and now she is doing a program manager job in CO2 sequestration in Scotland. And here is a teaser. I told you I'm going to keep it simple. So this is a picture I took some years ago, just behind the bus station here. It's just up here behind the parking lot. And there were this interesting fracturing in the tarmac. And that a kind of quiz for you is to figure out why I care about these fractures in this study. So I'm going to talk about the geology and the field and a few faults and fractures, and I'm going to talk about seismic reservoir monitoring in particular. I'll do a lot of effort on time shift analysis, detecting time shifts between or travel time change between vintages due to production, etc. So how are we doing so far? Is it okay? So as you see here in the kind of smaller box, South Arne field is really a ridge just on the in the western part of Denmark, just on the borderline to Norway. Luckily for them, it came in the Danish sector, but it is part of the system of fields kind of stretching from Dan and South Arne and then Val and Ekofisk, just going up there into Norway, and there they are sort of the same geology, much of it, and formed at the same time, and the same sequences, and the same geomechanics, etc. And you can see all the smaller Danish fields here. So much of the Danish oil is happening in this area here, and of the same causes. But much of it is kind of running quite dry right now, so it's kind of near end of production for most of it. And here is more a sequence of the layers. And interestingly, I'm not a geologist. I'm just like in geology. So you probably know more about this than me. But we are talking about the ecophyst formation, the ecophyst layer, and over that is the boulder layer, which is a shale, which is the seal. Ecophyst, of course, is the production zone, and there is also the Tor formation below it, I believe. We can see that here, ecophyst formation and Tor formation. And so it's much of the same geology as on ecophyst. And up here, the rig is here, but this is also the kind of dim zone, because in the north part of the field there's leaking gas up, so it gives a dimming to the seismic, so they can't really see much of what is going on below the gas cloud. But it's in a way, but it's still a good, at least in exploration, it's good to see a gas cloud, because that you know that you have a functioning hydrocarbon system in there. So there must be a source rock somewhere. So that's comforting. And in the middle here is much of the kind of where the production is happening. And here is just an image of the seismic volume on the baseline survey. And over here you can see the gas cloud, and due to the gas-filled strata is very high in attenuation, so you don't really manage to send seismic waves through it. So the only way to image below gas is by undershooting, meaning that, say, you have a source here bouncing down here and coming up there, avoiding travel paths going through the gas. And to the extent that you can see something below the gas, you can see that gas has a much lower velocity than fluids, meaning that the travel time going through the gas is much higher. So that gives you a pull down under the gas. So this trough here is not real. It should be an anticline. Anyway, so and you see the elongate structure here, and here is the top ecophyst, or the top of the ecophyst layer, and you can already kind of get some idea about the structure. So you have a four-way closure, but you also see that, say, on the seismic, you can see that there is a lot of faulting, and one of the key questions or uncertainties in the understanding of the field is to understand whether these slendering slow faults stop at the top chalk, or if they propagate down, and whether they are closed or if they're leaking or whatever. And there are loads of these faults, and higher up you have this polygonal faulting system in the shale here, making it complicated for, say, for drilling planning, because you don't really want to drill through faults if you can avoid it, because faults can reactivate and induce a sharing of the pipeline and break it. So you want, and in this case you can't really avoid drilling through some faults, but you can at least give some attempt of kind of minimizing the penetration, or to cross as few faults as possible. Here is the top Tor formation, just flipping, and you can see that, or in this area here, ecophyst disappears on the south side here, meaning that Thor and Ekofisk merges. And here is the base of the chalk structure. And the production is done by a combination of injector and producer wells. So they do WAG, meaning water, oil, emitting gas as injection, in order to keep up the formation pressure and in order to try to flush the oil towards the producers. And this image is from a former colleague of mine, Stavanger, etc., with also together with Buyback, as a geomechanics study where they looked at the geomechanical effects of production. And they had some interesting findings there. And to understand the geomechanics is very important, but because this is a chalk, and the key to good production is to have the production wells to cross the faults. And the faults or the fractures, and the fractures can be open or closed, and the state of them is depending on the geomechanical pressures down there, if they will extend or compact. So back to top Ekofisk. Here is just another view of it. Over here in the far end, you have the gas zone with a pull down, and this is more to give you a topological understanding of the field, because as I said, geomechanics is very important here, and what you're looking at here is a surface, but the color here is the inline dip in a grayscale color, showing not the amplitude map, but the dip of the layer, highlighting the profile of the structure. So one thing which is kind of important or useful is to look at these kind of side ridges here, and also the corresponding structure on the other side, and how this kind of whole structure kind of have a bit of an S shape. That can give you some indication of how this anticline was formed. So that is again other clues to how the geomechanics impact the faulting and the well planning. And here we also have another view of the overburden, and also in particular the faulting of the overburden, and how they say get into the reservoir zone, or maybe not. It's hard to say. And of course, the migration, hydrocarbon migration pathway is coming along like this, following the red arrows and accumulating, of course, on the top of the anticline here. So and here is the top of Ekofisk again, the dips, and what we are again looking at the inline dip projected, and here is a zoom out of the top Ekofisk, focusing on this area in this region with full scale, without kind of clipping or scaling down, downscaling of the image, as you often get in a 3D view. So and this is interesting. But because this tells you a lot about fracture directions, and where you should plan to insert your wells. But because again, you want the wells to cross as many fractures as possible, and that can get us to our riddle. So here we are back to the tarmac behind the bus station here, and how it does relate to South Arne, and it is of course these the patterns of these fractures here. I'm not a structural geologist, but I like geology, so I've been kind of reading up a bit on it. And do you have a name for this? Does anyone have the name for this pattern? What?
120 and 60 degrees rating angles are probably around 120 and 60.
Yeah, but it is a classic pattern in structural geology, and it's almost Riedel shears. So this is a kind of classic formation of faults, and that.
We need to report to Stavanger kommune.
Yeah, but I have a landslide there, but that's the source of it. But because you have a Riedel shears, you get that when you have an extensional system combined with a rotational system, which gives you a shearing and an extension. So that means the fractures are open, but they get a sinus shape, like you see down on the figure here, and that is what you can see here, and you can see here. That means that we can infer a lot of reasoning about the nature of the faults and how the faults and fractures were formed. And you can infer that when they were formed, they were open. But that doesn't mean that they are still open. Because they can be cemented. It's hard to say. But in the beginning, that they were open. And that there is reason to think that it's also about timing, that they believe that those who fault fractures which got oil filled early, they did not cement, but those who did not get filled that quickly, that they cemented before they got any charge. So this is how people sit and discuss anyway, and try to ponder and figure out a good way to get things out of it. It's a riddle, it's a quiz to do work on these reservoirs. And here is just an example of a coarse image of attempt at understanding the overburden of faulting. We did much better work on that later, but this was reported in a separate presentation, and I'm not going to cover that work from here of overburden fault mapping right now. But after this work was done, there is of course a lot of work happening on machine learning approaches as well for automated fault overburden or structural fault interpretation. So until now, I only been talking about the static properties of the field. So, but as they produce, it was, I guess, put in production in like 1995, and at least that was when the baseline survey was shot, and the monitor survey, Q Marine, was acquired in 2005, and these are the two vintages I'm focusing on right now in this work. So here is a seismic from '95, and this is on the flanks of the anticline, and this is in 2005. This is time-dated seismic. So you can clearly see that the layering is changing, or the travel time is changing, and that means that the velocity, there has been a velocity change or a contact movement or both, and we see time shifts not only in the reservoir but in the overburden and in the underburden, or meaning below the reservoir. And sometimes we see time shifts on the sides of the reservoir or on these flanks of the production zone due to stress arching. So stress and velocity, that they really belong much together. So the changes in the overburden is due to injection, that they are actually increasing the pore pressure beyond the virgin state, meaning that you're almost pumping up the reservoir like a balloon, and that is trying to expand. So that tries to lift the overburden, and that leads to a compaction there, or a higher stress, which leads to higher velocity, and that impacts the travel time. And the same thing can say inside the reservoir. If the pressure goes down, the acoustic coupling between the grains goes down and the velocity goes down. But also, and that is happening when you're doing injection. So typically when the pressure goes up, then velocity goes down. But there are other effects as well. I mean, if you replace oil with water, then you have the opposite effect on the velocity. So sometimes these velocity changes or combined effects, they are competing. But in this case, we had a favorable kind of impact or contribution on the velocities. And again, as you see, but what you also see is that the time shifts are not vertical. You would think that the time shifts would go down. They don't. The time shifts, they follow the layering, which you clearly can see here. And here is a small cartoon trying to explain why that is happening, and that is down to the effects of migration on your data. What does time migration really mean from a imaging perspective? So that means that you are taking, say, experiment here. This is observation, and this is how you see it. And migration will try to kind of restore the original structure. But so if you have here is two different cartoons. So if you have a flat layer, you have a velocity change here, then you get say a pull down effect, and that is vertical only. But for a dipping layer, then the travel time will impact along the travel direction. So that's the time, the shift will be a mix of vertical displacement and lateral displacement. But migration will lead it to that a time migrated image is that it will simulate the image you will get with a kind of zero offset downgoing ray. And but when it gets into the ground, it will kind of roll and bend and follow the structure due to the bending through the layers. And I'm trying to illustrate that by this is a ray tracing or a streamline of the orthogonal tangents of the dips, or the tangent vector for the layering everywhere, just to illustrate where the ray paths are actually going, and or the zero offset ray paths, and that means that if you get a time shift here, then the time shift will actually move in this direction. Same thing here. A velocity change here will lead to a time shift in this direction, which is a combination of vertical and lateral shift. And we have algorithms which can quantify this based on the fluid flow concept physics. And in our case, we used an algorithm called non-rigid matching, which is an image registration algorithm which has been tuned to work on seismic data. And there are many different algorithms to do that. Professor Dave Hale at Colorado School of Mines, he has done a public domain version or public source code for a 3D version as well. So there are different means of doing it. So I'm doing, in this case, I'm testing out 1D matching and 3D matching on these two volumes, and trying to figure out what the difference between 1D and 3D match is. So in order to do that, I take this, I'm just following my phone. I'm streaming through my phone, so it's almost getting low on battery. But I think I should manage throughout here. So I take this seismic image, and then I do warping on it. I shift the whole volume a quarter of a bin in the inline direction. So if you can see here, I just take the whole volume and just move it a quarter of a bin in inland direction. So that is my artificial monitor survey, and this is in order to kind of understand the detectability of time shifts and this lateral shifts. So if they use the input as baseline and the artificial shifted volume as a monitor, and I apply 1D time shift estimation on it, this is what I get. And it's obviously just noise. And that is because of time shifts will not honor the impact of lateral shifts. That means that if you have repeatability issues, if you have problem with a repeatability of a line, that will introduce noise like this in your volume. But if you instead do 3D, and here is the histogram of the errors, and this is all noise due to using a 1D matching method on a 3D problem. So, but when we do 3D matching on it, and this is the output of the 3D non-rigid matching, and you see that the DT, the vertical component is 0, and the crossline component is 0. The inline component is 6.25 meters exactly. So that means you can precisely calculate the lateral displacement vector from an arbitrary application or this deformation. And so then when we have established that 3D matching actually works on this data, on this quality, and on this say bandwidth, or meaning frequency range, and then we can look at the real data. So this is the input seismic, and this is if we do match it with the monitor seismic from 2005. This is the time shift we get. This is the overburden, and this is the time shifts along the top ecophysic horizon. And here you can see the blue color here. That means that there is actually a velocity change in the overburden, as we discussed, and that is due to geomechanical effect, or due to increasing the pressure in the reservoir, which means pushing up. That increasing the stress, that means the velocity goes up in this area here, and then velocity goes up, the travel time goes down. That means you actually get an uplift in that area, or an apparent uplift. And here we see some strings out as well, which gives a velocity increase. And here is the same using a 3D matching. And I hope we can agree that a 3D matching will give a much more accurate presentation and credible understanding of the effect in the overburden and in the reservoir. So we have much more kind of well delineated blobs along here. And if I had projected the production boreholes and the injection boreholes, then you would see that it makes sense. And this is the high resolution version of time shift, but you can also parameterize it on how smooth you assume that the time shift will be. And this is the long wavelength version of time shift in 1D and in 3D. And then we're talking only on the vertical component here. So you still, and the long wavelength shifts, that I will focus on the say velocity changes, and not so much the kind of local contact changes, which are low frequency in nature or low wavelength. And let's look a bit more on analyzing these time shifts, and this is in the overburden. This is in the shallow at time slice at 500 milliseconds. And this is the estimated displacement, and you see the unit here in meters in this color scale. And the colors here indicate movement to the left or to the right. And here is for along an inline. So red is moving up and blue down. And here is the vertical component. And you can see that there is not so much acquisition footprints in the inline and crossline shifts, but there is certainly a lot of acquisition footprint in the vertical component in the shallow here. And we can plot this as well in the how the acquisition footprint distributes in the scale. So this is quite useful kind of analytics, say for understanding the quality of your acquisition and processing. But because you can do all sorts of things in order to try to mitigate these footprints. But then we also have lateral shifts. So here is the inline shifts, and here are the crossline shifts, and here is the vertical shifts in 3D. And again, we see that a lot of the changes are happening over here in this area, but we have also changes happening along the flanks or the ridge here of the structure. And this is the vertical shifts. Vertical shifts. So this is just a vertical component, but if you instead try to calculate the shift along the surface normal, that is what you get here. And compare it with the 1D shifts. And here it's getting a bit more complicated. So here we're getting the closest to equations today, I guess. And this is these are the for a dipping layer. These are the real tangentials or shifts shifting along the normal. So it's a time shift in time migrated data is a 3D vector. If you do a 1D matching instead of a 3D matching, then you will always overestimate the magnitude of the time shift for the dipping layer. And if we look at the observed shift vector, what we can do and what I did is to calculate the surface normal by calculating structural dips and finding the tangent, and then projecting the observed shift with the time shift along the surface normal. And that is the tangent shift. And in order to calculate the time strain, and if time strain is a complicated thing or to talk about, but because there are so many subtleties there, but because time, if you take the derivative of the time shift, you get the time strain, and that gives you the delta B, which is the change in velocity between the baseline and monitor. But that only applies if there are no formation changes, meaning changes in thickness of the layers, or say a fluid contact moving up or down. And that equation is only valid if there is a pure velocity change. But that is anyway what people are mainly focusing on, the time strain. And so I'm arguing that, or we are arguing that a more accurate measure of the time shift is to calculate, and the time strain is to calculate the time strain along the surface normal. And we also have a shear shift here, which is more like an error term, which are also useful to look at, but I'm not fully I don't fully appreciate all the impacts of it. And now I'm getting into more towards the end of the slides here, but here we see seismic in 95 and 2005. And here is the time strain we get using 1D matching. And this is the top ectofisk, top tour, and this is the base tour, meaning the base of the chalk. And you can see that this red blob here indicates velocity increase. But of around 3 to 5% delta V, which is the ratio, of course. But you see that it's almost on the same scale as the noise around it. So this is from time strain or the derivative of the vertical component of 3D shift, and it's much less noisy. But you also have removed a lot of the 4D effect. But that's so. If we then calculate the time strain, tangential time strain, then we are getting back to this image. And compared to the 1D version, it is much more accurate. It is mostly confined into the tour layer. You have something over here, and you have much less ambient noise in the host rock around it, overburden and sideburden. So that is comforting. But it's still taking a derivative, so it will kind of be sensitive to some noise. And then I know I'm getting towards the end, so I see time flies here. So just to have a quick look at the amplitude changes at the same time. So here is 95 with minus 2005, and the difference in amplitude. And you see that you have changes in amplitude, not only inside the reservoir, but also below the reservoir. And this is, if we apply the lateral or the 3D shifts to the monitor survey, so we calculate the warped image in 3D, long wavelength on the 2005 vintage, and this is the amplitude change you get. And this is actually a very interesting image, or kind of it tells you a lot. First of all, it's good to see that there is hardly any 4D signal in the overburden and underburden, and all the changes are actually happening inside the reservoir. So, and much of it is happening here in the interface between the ectofisk and tour formation, and corresponding opposite polarity signal in the tour underburden layer or interface. And then if we look at the amplitude differences from above, this is what you get. And it's kind of interesting patterns here. I don't want to spend too much time explaining it. What I wanted to show is that if you overlay that with the fault predictions or the fracture predictions, then you can see that the amplitude changes are very much honoring the boundaries of many of the fractures you have detected there, and many of them are bound, and some of them are not bound, and that is interesting, because that tells you something about connectivity. How far do you reach with a production well or in the injection well? I mean, before you get to a flow barrier which inhibits flow. And this, I'm not going to talk here about how we detected all these faults, that they are covered in a different paper. It was explained in detail in a publication called Oilfield Review from some years ago, and done by Donatello and myself. But in this time, this was done on together with ADNOC and some other companies in the Abu Dhabi, Emirates region. And the workflows are more explained there. And that conclusion. So 1D matching is sensitive to lateral shifts, and velocity changes in dipping layers will introduce lateral shifts. So 1D matching will overestimate the time shifts, and the vertical component correspondingly will be smaller than the true time shift, because part of it is captured in the lateral displacement. And tangential time shift is a more accurate measurement. That is the end of it. So, final slide. So, any questions? Yeah, Lothar.
Thank you very much for the very interesting presentation. A student on university, he was working on the same project. One question, in the trend, you can calculate the time shift between two cubes. Is it calculating the vertical time shift, or does it take the lateral shift into account?
Well, there is seismic trace alignment tool, and in Petrelli is only doing the vertical. Yeah. That said, I know that because I implemented it, that there's a flip inside there in the code. So the 3D version is really there, but someone has to flip the button in the code, and also extend the interface to take additional outputs.
Another question. You say that you say sometimes you talk something about fault, sometimes about fractures. I personally get the impression that seismic cannot see fractures. When I have a fracture measurement along a fault coming from FMI interpretation, and I try to correlate it, for instance, with fault net coming from arm tracking, for instance. Even if I'm very good with marketing background, I don't see a correlation. So there are two different types of resolutions in my view.
Yeah, well, you have a point there, and I'm a bit sloppy in the distinction between faults and fractures, because a fault is a fracture with a throw.
Yeah.
So it is sort of the same thing, but to image a fracture without a throw is kind of difficult. Depends if you're lucky with the azimuth or shooting direction, if it's shooting parallel or orthogonal to the fracture, but there are, the seismic can react to it. So you have diffraction imaging, and you can also look at azimuthal anisotropy in order to infer these fractures. But in general, you are right. It's hard to detect, say, fractures on seismic. But on the other hand, when you have worked on geology for a while and understand the underlying concepts of what creates faults and fractures, you can really infer the presence of fractures by the presence of the faults, because faults often have conjugate sets. So you know that they have to be there. So for instance, in this example, typically in where you have anticlines like this, that depends on the stress direction, and we see this a lot in the Middle East. And in the Middle East, you have much worse seismic, but because you don't have that high frequency. So often when you look at a structure, you can just infer that there is a flower structure fault system over an anticline, and you can make that a hypothesis. So even though you don't see it, you can infer that it has to be there, and then you know the azimuths of those fractures. And so that can be your hypothesis, and you can drill, and then can see if your observation confirms your hypothesis.
Thank you.
It's a very good presentation. I have a question regarding the velocity modeling. So, what do you think about what we do on is processing the data from like the different time and using the same velocity model? Yeah, especially in chalk or something where you have convections.
Well, I understand what you're saying. So say for instance, if you do time imaging, time migration, and you're using the baseline velocity model for both images, then it's easy to do analysis like this. If you instead do update your velocity model and you re-image the monitor, then you actually take away a lot of the 4D effect, because some of the 4D effect is inhibited or instead captured in the velocity field. So you have to include both the velocity field and the seismic in order to do a full reasoning. And usually the baseline model is good enough for processing of the monitor, because okay, the velocity model is not super perfect, but it will still give you a robust imaging of the reflectivities. So you will still maintain your focusing of your migration operator. I see there is some work now. Some service companies are experimenting on 4D FWI, which outputs an image in depth by default. And I don't know enough about the details there, how these algorithms are implemented, what they actually do, but I hope and trust and beg that the 4D effects you see in the acquired data is actually captured in a delta field in the FWI. If you don't, then you will actually kind of knock out some of the 4D effects of the data. That is not good. And but I also see problems with say 4D FWI, which try to do this magic capturing all in one, because very often it's very hard to say if time shift is due to a velocity change or due to say a fluid movement. So you have to be very careful there. It might be better to under-assume than over-assume.
Also, there is some limitation from inversion in terms of the vertical resolution.
Okay, another question?
Regarding the radial faults, do you think it's a local shear situation in that field, or it could be part of a greater strike-slip system? Oh,
it's certainly a part of a greater system. I mean, the Torf or the Valhall and Ekofisk and all these kind of further north, they are part of the same kind of tectonic kind of stress regime on a macro scale. Yes.
How much of these workflows are done manually, and how much is like automated using machine learning, intelligence?
This is done, I wouldn't say manually, I would say it's deterministic, meaning that they are using deterministic methods funded by mathematics and physics bound. What I've done now here is not based on machine learning in any way. I see that there are companies now, and I see there is a lot of research papers coming out with using machine learning for time shift estimation, 4D analysis and things. And to be honest, right now, from what I've seen, is that first of all, I think it's overkill, because we have good physical methods to solve the problems. So in order to use machine learning to solve it, it is just knocking in an open door. to some extent. And I would also be very worried about these machine learning attempts, because they are very often done by transfer learning using synthetic data to train the models. And then these synthetic models are often made by data scientists which has no clue about geophysics or imaging. So do you really trust that their training data or learning data is physically plausible? Yes.
This is Sean from the University of Stavanger. Yeah, I noticed that you saw this major time shift at the flank of the anticline.
Mm-hmm.
And it's quite interesting that you conclude the time shift was caused because of the dipping of the strata. Have you saw any like a sensitivity of this time shift can be related to the change of fluid content after 10 years of production?
Obviously, it must be a combination. The lateral shift must be a combination of dips, structural dips or strata, and some actual physical 4D change in the layer, which can be either velocity change or a saturation change. We have studied. We have tried we have algorithms or workflows in order to try to distinguish between velocity changes and saturation changes, but that is not covered in this work here. But I have other papers where we do demonstrate that we can separate saturation changes from velocity changes. And the short story there is if you have a velocity change in a layer, it will not only impact that layer, but it will impact all layers below. So you will get a curtain effect on all layers below. But if you only have a saturation change with no velocity change, then you have a shift only in that layer and in none of the surrounding layers.
Yeah. And by the way, may I ask what was injected for the production versus brine or smart water or CO2? It
was WAG, water alternating gas. What sort of water? I assume it is brine, but I don't know.
Right. Thank you.
Hi, is it worth investigating the change in the elastic properties of the ecophysical rock where you see these velocity changes to sort of work out whether we might see more deformation in processes like this?
Oh yeah, absolutely. And there has been a lot of work, and this has been well documented also on the South Arne field by Jörg Hervanger, which is a world expert on geomechanics, and Ole Weibeck. And they have demonstrated they have observed anisotropic velocity changes in the ecophysics, and which is happening. And the only reason that can happen is that they have stress reversal, meaning compacting areas which kind of flips and become expanding. And that of course can have, if those stresses are big, changes are big enough, that can impact the opening and closing of fractures and production.
Thank you very much. Any more questions?
I think it's time for a beer, at least for me.
Thanks again for coming today, and Victor, that was a really great talk. Technical, but with very good explanations, and I love structural geology, so the streets were just a pleasure for me to see. And I can notice that we starting to have people who attend our meetings regularly. Thanks a lot for your support, and please come more on our subsequent meetings. We also will have online meetings. And I really hope that you will come to Oslo annual, because there we will have our special session, and it's going to be a great event. Thanks a lot.